Section H3, conservation of energy. Now let's look at the first case, conservative forces. We have seen in the last section we could write down the energy as the kinetic energy plus potential energy, and that's going to be equal to a constant. Therefore, any change in total energy, which would be the sum of the change in kinetic and the change in potential, is zero. Because if you take a delta, if you have a constant, you take a delta on the constant, you get zero. So here you can see that the change in kinetic energy is minus the change in potential energy, and vice versa. The change in potential energy is negative the change in kinetic energy. They change form. So you can think of the case where there's the ball that's at rest at a height h, so that's mgh, and then as the ball falls, it loses its potential energy and it gains kinetic in the same fashion like this with the negative sign, so that total energy is the same in all places. And we have seen in the last section, we could say then the energy at point 1 equals the energy at point 2, or a lot of times I like to just say before and after. So whatever suits you, you can do this. You could also say the initial energy is equal to the initial is equal to the energy final. So the initial energy equals the energy final. So whatever you prefer when you solve problems, they're very, very helpful in problem solving. Now, if we look at non-conservative forces, let's say, look at a problem with friction. Friction's always going to work against you, and the work due to friction is going to be negative, say, F times D, where this is less than 0, because, see, the friction is working against you. So if you are moving, say, to the right like this, the friction is going to be in reverse. So if I had the friction force pointing to the west and you're moving to the east, then the definition of work as the force dot, distance, the distance vector is to the right, but the force vector is to the left. So that would be here FD times the cosine of 180, and that's equal to a minus 1. So you would get minus FD. My F here is the magnitude of the force, so when you put the minus sign in front, it's less than 0. So if we have a problem like this, we have to put it in by hand. Suppose we have a kinetic energy at point 1 and potential energy at point 1, and then some friction is done, minus FD, and then this is the kinetic energy at point 2 plus potential point 2. You see that not all of the original kinetic and potential is available at the second point because some of it went away in the form of friction. So we can do problems with friction, we just have to be careful. We can't write down the energy at point 1 equals the energy at point 2 with the kinetic and potential. We have to then put in the friction by hand. So energy is always conserved, and in the old days they thought they had two principles of conservation, that the energy is always conserved and that matter is conserved. That means you can't create or destroy energy, it just transforms in different ways, and you can't create or destroy matter. You might break something in half like a cookie and have two pieces of matter, but you didn't really like make anything disappear. But Einstein showed us that you can make something disappear, matter, and you get equals mc squared. In other words, there's energy in the form of matter. So now we have one principle, and that is energy matter is conserved. The combination, the conservation of energy matter or matter energy is conserved. One conservation law, while in the past we had two. And then Einstein's relativity theory dates to 1905, and not long after, when he proposed the theory, he derived that equation.